Hi, my name is Craig Noah, and in this video I'm going to step through an integration problem using the method of integration by parts. Here's the problem I'll be solving today. I'll first start by saying that with a complex integral like this one where there's more than one function of x, it's not always intuitively obvious with which method or approach to use to solve the problem. A checklist I go through is 1. Can we use u-substitution to simplify this integral? And in this case we cannot, because both functions of x are raised to the same power, and u-substitution will not yield us any cancellations. 2. Does this integral look like any of the trigonometric forms that I have memorized or so I can substitute in for? And the answer to that is no. So third and lastly, I guess the last resort, is the notorious integration by parts formula, which says that integral udv is equal to uv minus integral v du. And from here, I'm just going to designate these variables and plug and shove. So let's set u equal to x. That means we have du dx, the derivative is equal to 1, and dx is equal to du. And I'll just say quickly, I did set u equal to x for a reason, and that's because, well, essentially the point of the integration by parts formula is to take a messy, complicated integral like the one we have here and transform it into a more manageable integral that we can solve efficiently. And so by choosing or setting u equal to x, I look ahead and I see du is going to appear in our new written integral. And if I want this integral to be simplified, what's a u that I can pick so that the derivative of that du will be simple, thus making the new integral simple? And so if I set u equal to x, the derivative of that is just 1. So that will likely lend way to a more manageable integral. However, you can designate u to be whatever you want and guess and check, but this method, kind of projecting forward and making an educated guess, is going to save you a lot of time. And so now I set dv equal to 1 over root 1 minus x. And now I have 3 of the 4 variables. I just need to solve the integral of dv to get the last of the 4 variables to substitute in. And so that will be the integral of root 1 minus x. And to solve this integral, just quickly, I'm going to use u-substitution. I normally do this in my head, but for the sake of visualization, I'll demonstrate it here. And just note that the u and the du I'm using right now in gold are different from the u and du from the integration by parts formula. I'm just doing this as a quick aside to solve for v. So du dx is -1, dx is equal to negative du, and so v is equal to, now rewriting in terms of u, we have 1 over root u, dx is negative du. So let's rewrite this. I'm going to move this -1 to the outside of the integral, which you can do with all constant coefficients, and rewrite u in terms of an exponent. So we have u to the 1/2 du, and this is manageable. Excuse me, this should be -1/2 because that u's in the denominator. So we have -1/2 plus 1 is 1/2 u divided by 1/2 is 2 times that -1 out in front. So we have -2 u to the positive 1/2, and we set u up here equal to 1 minus x. So we're going to get v is equal to, let's go ahead and put this in the square root, u was equal to 1 minus x. So we have -2 root 1 minus x for v. And now we have all 4 of the variables that we needed to plug into this integration by parts formula. And so let's copy that down here to have a point of reference. And now, plugging in to this equation, we had u equal to x. We had v equal to, right here, negative 2 root 1 minus x minus integral v again, negative 2 root 1 minus x. And du, if we remember, was just equal to dx here. And now, like I was saying in the beginning, this integration by parts formula has given us a much more manageable integral this time around. Only one function of x in the numerator. It's much nicer, and we can solve this efficiently. I'm going to rewrite this now. I'm going to clean it up. And again, I'm going to move this constant coefficient to the outside of the integral. The minus signs will cancel. Be left with integral 1 root 1 minus x. And again, this is much nicer to solve. So solving that integral, combining it, the initial uv, I'm going to get, and again, here I'm just going to use a quick u-substitution, but I do this part in my head just quickly with enough practice. It's easier and quicker to just do in your head, but if you'd like to write it out, I use the same approach as I did up here in gold, where I set u equal to 1 minus x. And from there, differentiate it and plug in, but essentially this is going to be equal to a minus 4/3 because it's going to be a negative du, and then you have 3/2. So 1 minus x to the 3/2. And now this would be the answer if this was an indefinite integral. This plus a constant, I should say. However, we are tasked with evaluating it on the interval from 0 to 1. So let's plug in first 1. So we have negative 2, 1, root 1 minus 1. That's going to be 0. Minus 4/3, 1 minus 1, excuse me, that should be 1 to the 3/2. And again, that's going to be 0. Minus, now let's plug in 0. We have negative 2, 0, root 1, that's going to be 0. Minus 4/3, 1, minus 0 is 1 to the 3/2, which is just 1. So these negative signs will cancel out here. And we're going to get 4/3 as our final answer. And so now let's go back up to the top and write in 4/3. So what this is saying is, on the interval from 0 to 1, this function converges to a value of 4/3.